November 2nd, 2021. Just a reminder, we are gonna have an exam today. It starts today at 7 p.m. Go until tomorrow. The window is open until tomorrow 7 p.m. You gotta pick up your 2-hour window within this period. Make sure you start the exam no later than 5 p.m., right? Otherwise, you're not gonna have 2 hours to finish the exam. And we finished conservation of energy. The deal is the same, right? We do not have a lab for the Tuesday class today, for the Tuesday students today, right? So, when it's 6:50, we just go home and do the exam. Okay, finish conservation of energy. Oh, chapters 5, 6, 7, and 8. 5 is laws of motion, applications of laws of motion is 6, work is 7, conservation of energy and applications of conservation of energy is 8. So what we are going to start today is linear momentum. Okay, and let's get words. No, let's get the other documents here. Got notes. Okay, that's the. Okay, we finished. Okay, we finished the first volume of my notes. The first volume of my notes go only until chapter 8, and then it starts on chapter 9. The volume 2 starts on chapter 9. I had to break it down because if I publish something too big that Amazon.com, they charge too much to download it. That's why I had to break it down. Let me see if I have the volume 2. I don't think I have the volume 2 here. Google Drive. Yeah, I have to do that. If I don't have it, I have to do that on the fly. Go. Google Drive. Still not working. Yeah. I'm gonna reset it, okay? Let me reset it. I don't like these other ones not working. Yeah. Add slides. Add notes. Yeah, I don't have volume 2 here. I'll have to bring it next time. But anyway, I can do that on the fly. And that projector, the red light is still red. Oh, really need to get. That one is red too. That one is flashing, but this one is not flashing. Just working last time, right? Both projectors were working last time, right? Yeah. I'm not gonna waste too much time with that. Hello. Okay, so let's see if it can go. Okay. Linear momentum. Coming? Yeah, it's coming. Okay. Yeah, that one's not on. Doesn't matter. Okay, someone gotta tell IT about that. Okay. Linear momentum. Day is 11:02:21. Chapter 9. Linear momentum. So it is. Okay. So how do you define linear momentum? Linear momentum is an important quantity in physics, and there is a reason for that. That's why we define it, okay? Here, let's write it down. Linear momentum, abbreviated by the letter P, is an important quantity in physics. That's why we define it. That's why we define it. Okay. Cops use linear momentum to investigate the scene of a crash. Okay, so that's one of the applications of linear momentum. And if you watch Interstellar, okay, when they were nearby the black hole, and he wanted to propel the other ship, you know, they were using also conservation of linear momentum there. They want the main ship to get a boost, and they separated two of the other spacecraft that was in the ship, right? Do you remember that part there in the movie? And then the guy that the commander of the mission that was in there ended up going to the black hole. Okay, and the other ship that was in there got the boost enough, got enough boost to reach the planet that they want to reach. And no, it's all related to not only to Newton's law but also to conservation of linear momentum. The definition of linear momentum, don't forget, linear momentum is a vector. And I'm going to show you why linear momentum is important. Linear momentum is a vector, so you have to put an arrow there at the top. Okay, go, P, MV. There you go. That's linear momentum is a vector that's proportional to another vector, V. M is not a vector, M is a scalar. Why is that? Why linear momentum is important? Well, linear momentum is important. Linear momentum is important because of Newton's first law of motion. Okay, that's why. If, in other words, if the net force is equal to 0, comma, then linear momentum is conserved, just like energy is conserved. Okay, okay, so in other words, if net force is 0, comma, acceleration is also 0, and the velocity vector is constant, or you can also say, or conserved. Okay, because that, of course, I'm assuming that the mass remains the same, because P is directly proportional to V, then momentum is also constant. Okay? That's the obvious example. Net force is equal to 0, but then there are the not so obvious example that we discover out there. Let me get the PowerPoint here for you, so I can illustrate that for you. I'm gonna just repeat in figures what I told you in words. Maybe this one. Okay, we go. Uh-oh. Maybe go back all the way down here. Ay, 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 ay. Maybe here. See. Yeah, going down. That's work. Oh yeah, that's where you want. That's where we want. Okay, so here you go. Okay, assume that we have the situation in which a block is moving its constant velocity and there is no friction whatsoever. Okay, here you go, concurrent slide. If there is no friction, the mass of the object is not changing, the net force is equal to 0, right? The object will continue moving with the same velocity as time goes by, right? Here you go. Just like I have here. He's initially here, later on he's here, later on he's here. Since the velocity is constant, momentum is also constant. We say that momentum is conserved, just like energy was conserved, mechanical energy was conserved. Since momentum did not change, we say momentum is conserved. That's the situation. We can prove that mathematically, by the way. We can prove that mathematically. Okay. You know, prove mathematically. Here, just blah, which was just blah 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 here, right? But now we can prove mathematically. We can prove mathematically the following: if net force is 0, comma, then linear momentum is conserved. You can do that. Let's do that. Okay. We do know. We start with Newton's second law. Oops. Oh, no. Oh, nope. Interesting. Okay, like that. Net force is equal to MA. But MA can also be rewritten as dVdt. dVdt. And I'm going to put my M outside this guy here. But because M is constant, we can here write like that. The differential, the derivative of mv dt. But the mv dt, according to our definition, is what? P, right? So that's the relation between net force and P. There you go. That's the relation between net force and P. If net force is zero, okay, then we have the following. Copy and paste, right? Which means that for this special case, the following. Nope. Oh gosh. Yeah, here you go. Means that P is a constant factor for this special case. Or momentum is conserved. That's what it means. Like I said, there is the obvious case in which the mass is moving with constant velocity. There is a special case in which a single mass is moving with constant velocity over a frictionless surface. With a net force of 0. In this case, we still have conservation. Of momentum. But then, physicists are smart people, okay? But then there are some not so obvious situations in which this same result can be taken advantage of. Okay? And those are what we call the innovative thought, innovative way of thinking. Okay? It's not obvious, but when you discover it, becomes obvious because it's so simple. That's the difference of something, being obvious in, how do we call it, in hindsight. Okay? It's like the wheel, right? The wheel, in hindsight, oh, such a simple invention, right? The wheel, right? The one that rolls. And yet, the Mayans, the Aztecs, they didn't have wheels when the Europeans arrived here in the Americas. The conquistadores noticed that the Aztecs didn't have wheel, haven't been able to invent the wheel, even though the Aztecs were at a cultural level very similar to that of the Egyptians. Okay, even though they were at an advanced level, maybe even of the Greeks. I think the Aztecs had a culture similar to that of the Greeks. Think about that. The wheel was invented before the Egyptians. The wheel was invented by the Sumerians. And yet, that invention that was so obvious to us was not obvious to them. Right? So let's take a look here. And this thing about conservation of momentum, you know, can be applied to some problems in an unobvious way, in a way that's not so obvious, which is a very important way. Okay, so let's take a look at our, here you go, there is this situation here. Now instead of having just a single object, let's think about two objects interacting with one another. And I'm going to show to you how we can take advantage of the concept of conservation of linear momentum. Okay? At this point, remember, at this point you already learned about free body diagrams, right? So we're going to apply free body diagrams here too. But I'm going to do the following. I'm going to choose I'm going to choose how the free body diagram is applied. I'm going to choose which object is going to have a free body diagram, so you can understand the importance of conservation of momentum and how it is used. Think about that two objects, and I am zooming into this object. I'm applying my free body diagram to this object here. I'll call it my system. Even though we have two objects, this object alone is my physical system. This is the one that I'm going to keep on watching for forces and velocity and so on. Okay? So here you go. This object is approaching the other one. He's moving with frictionless, right? Now over a frictionless surface. He's approaching the second one. The first object is moving with constant velocity. The second one is at rest. And then they are going to interact with one another. Remember the idea of interaction from Newton's third law? What does it mean? They are going to interact with one another. This first object is going to apply a force on the second object. And I'm going to go even further than that. I'm not going to, gosh, I hate that. I'm going to put this force here. I'm going to dash this force. Here we go. So you understand that I am looking not at the second object, but I'm looking at the forces applied to the first object. Like that? See that? This force here is the force of object 2 in 1. Okay? Force of 2 in 1. F21. The other force is force of object 1 in 2. F of 1, F12. And then what's going to happen? They're going to interact with one another. We're doing the simplest possible possible collision that we're going to see out there. The two objects have the same mass, and then what's going to happen next? They're going to stick to one another. Okay? That's the simplest type of collision that I'm going to see out there. They stick with one another. It is as though as I have put a Velcro between those two objects. Can you picture that? Male Velcro here, female Velcro here. Okay? They undergo a collision, they stick to one another, and they move away. Okay? Velcros are pretty good for this type of experiment. I used to do this type of demonstration with Velcro. Okay, now what you have to know about this thing? You do know that while this first object is moving towards the second one, you know that momentum is conserved. Velocity is conserved, and consequently linear momentum is conserved, right? But the moment that it impact, why is that is conserved? It is conserved because the net force is equal to 0. However, the moment that it experiences a force, momentum conservation ceases to exist in this object. Okay? And momentum is no longer conserved. From now on, from instant 0, before it collides with the second mass, to after the collision, momentum was not conserved for this object. Do you agree with that? Okay? Everybody can picture that? Now, that's when comes a smart way to look at this type of problem. Okay? What if, instead of using the first mass as my system, what if treating a single mass as one mass, we start thinking of the two masses as a single mass? That's what the question that scientists made, physicists made, when they start looking at this thing, okay? What if I consider the two blocks as being my system? What if I consider the two blocks as though they are one single mass? Okay? A single mass that expands and contracts. Why is that? Because as time goes by, see the box contracting here? If it undergoes a collision, right? If you are smart enough, you are going to realize that if you treat those two masses here, you are going to realize that momentum is going to be conserved even after the collision. Okay? And I'm going to show to you why. Here you go. The two masses are our system. The two masses behave like a single mass. This mass is approaching the second one. The first mass is approaching the second one. There is a collision here. Look what's happening. Second mass is applying a force to the first mass, and first mass is applying a force in the second mass. Now, because the two masses are being treated like a single object, or let's say are being treated as our system, the net force in the system is going to be what? Do your math. Referring to Newton's third law of motion. The net force is going to be what? Huh? I want to hear from you. It's going to be 0. Okay? And so, because the net force is equal to 0, there is no friction, remember. The two masses can move merely together with each other, and we can find out what's going to be the final velocity just by applying Newton's first law combined with the definition of momentum. Okay? Make sense? So now I can come by and say, look, momentum at this moment is going to be equal to momentum at this moment here. Oh, why did I put 0? It's not 0. Okay, momentum at this moment. Okay, I gotta put a... Here you go. Okay, so here you go. Momentum at this moment is going to be equal to momentum at this moment because the net force is equal to 0. And it's going to be equal to momentum at this moment again because the net force is equal to 0. How do you solve for this problem? Using momentum. How do we find out the final velocity of my system for this special type of collision that we call inelastic collision? Okay, so let's write that down here. That is, we're going to start, here you go. We are going to start investigating the simplest example of the simplest application, not simple example, but the simplest application of conservation of linear momentum. Okay, the case in which the two masses have the same value, the case in which two masses have the same, and they undergo what we call an inelastic collision. Inelastic collision. Okay, what do you mean by inelastic collision? They stick to one another as though as there was a Velcro in their on their surface according to the drawing. So example, okay, example. Let two masses of same value m. The first mass is moving over a frictionless surface with constant velocity towards the second mass, which is at rest. Okay, the first mass collides inelastically with the second mass, inelastically with the second mass. Find the final velocity of the whole set. Solution. Okay. Okay, so let's go here. You know, because there is because the surface is frictionless. The surface is frictionless, and there are no external forces. Okay. Comma. Momentum must be conserved. For example, the first mass is moving with constant velocity. I'm gonna put like that, v01. Subscript. Okay. Momentum must be conserved, or we go. What we write? We're gonna write something like that. We go. We're gonna write that initial momentum I want to do it a different way. Oh gosh, instead of 0 I'm going to put not is equal to final momentum, like that. And when I mean initial momentum, I mean initial momentum of the first mass plus initial momentum of the second mass. And when I mean final momentum, I do mean final momentum of the first mass plus final momentum of the second mass. Okay, like that. Initial momentum of the first mass, you should know, is what? You gotta, use what was given, right? M V naught 1. Initial momentum of the second mass is what? Is at rest, right? So you gotta be 0. Final momentum of the first, oh gosh, okay, got it wrong. Let me get this. Final momentum of the first mass mv final 1, mv final 2. Right? I'm doing this step by step because the collision is inelastic. What we have? Final velocity, and is inelastic. What does it mean? That they're stuck to each other, right? The final velocity of 1 must be equal to the final velocity of 2. Okay, and what we end up having? We end up having that this equation for conservation of linear momentum becomes simpler. I don't need a 0 anymore. We end up with 2m Vf1. We do not know Vf1, right? We want to find Vf1, and we go mass, cancel the mass. We want to find the final velocity of the two masses. Would you expect the final velocity to be more than the initial velocity? Tell me. Do you think, the final velocity of the set is going to be greater than v naught 1? Do you expect that? This guy is coming with the initial velocity, let's say 2 meters per second. He's going to collide with the second guy. This force that's being applied to this first mass is going to slow it down, right? Can you picture that? But the opposite force that's being applied to the second mass is going to accelerate the second object. Do you expect that the final velocity here is going to be greater than the initial velocity? Why? Give me a physical argument, not a mathematical argument, but just a physical argument.
Well, like in air hockey, if you
Like a what?
like in air hockey,
Air hockey? Uh-huh.
if something, yep, only takes the same amount or less.
Uh-huh.
Um,
You can think like that in terms of conservation of energy. Can you picture that?
yeah.
Okay. Yeah, that's right. It's not going to be more. It's going to be less. It's just a matter of how much less is it going to be. Otherwise, it doesn't make any sense, right? How come one mass that's moving at v naught 1, collides with another mass, and now you have this set of two masses moving faster than the single mass before? That doesn't make any sense, right? It has to be less. It's just a matter of finding out by how much more or less. Okay? So let's find out. We are almost there. Here you go. I want to find this guy here. I'm gonna highlight here, both face it, and Oops. Okay, final velocity is v not 1 divided by 2. Now it is in a bold face. Here. This one is not supposed to be in bold face, right? Oh, I forgot to put the vector there. But because it's one-dimensional collision, we don't need to keep on using the vectorial notation. That's one type. On the simplest example that I'm going to see out there. You can go ahead and do other types of collision, instead of M and M, you do this one would be M and this one would be twice M. Or this one twice M and this one M. Right? You can do like that. And then there is this other important type of collision that we're going to see out there. Okay? Which is somewhat related to inelastic. Okay, is what I like to call an explosion. We have two objects bound together, they're at rest initially, and somehow we manage to have the objects propelling each other. And I can tell you what type of situation you can have like that. Propelling each other, interacting with one another. We can have a situation like that. Here you go. Here you go. Yeah. I copied the wrong one. What about now? Oh man, it doesn't do anything. Is this the one? Huh. Huh. There's so many. Okay, looks like I got it. Yeah, those are the things that happen with Excel. With Excel now, it's PowerPoint. Uh, Here you go. Can you picture how something like that can happen? Two objects are at rest, and then suddenly they pull each other apart. Somehow they pull each other apart. And then they start moving away from each other. Okay. Okay, so let me get this one here. I put it here. I don't want that. Send back. Okay, like that. That's the type of, okay, here you go. They're still moving away from one another, see that? Do you see what I mean that this object is just kind of look like they are elastic, right? This system looks like it is elastic because it start uses a small size and they start moving away from each other and they start, it is as though they're stretching. The single system is stretching. I'm going to do a better thing here. Yeah, so we can have a better send back. Oh, huh, interesting. Yep, like that, like that. Like that. Let's play the movie again. It's very important, it looks like such a stupid drawing, but it's very intuitive. Here you go. Start like that. The force, you know. I want this guy a little bit more to the right, to the left. Here you go. Yeah, moving away. Yeah, here you go. I don't need that anymore. Okay, so let's, we have this. Can you give me an example of something like that? You have two objects stuck together and somehow bang, they move away from each other. What? Give me a real life example in which something like that would happen.
The pool balls.
A what?
The pool balls.
Okay, well, are they at rest initially, the pool balls?
They can. I mean, if
And
you
then
made it.
suddenly they're gonna move away from each other without doing anything? The pool
Mm,
balls? Think about that. I've got two pool balls put over the pool table, right?
right.
You leave them sitting there. Are they spontaneous? They're gonna move away from each other?
No.
No. So that's not a good example, right? So think about another one. Here you go. Right. Two objects stuck to each other, and then suddenly they move away from one another. Here you go. Here you go. I have my arm here, right? This arm is stuck to this other arm, right? And then suddenly it moves away from the other arm. Okay? I can consider that a sort of explosion. Okay? That's a simple example that I can do here in the classroom. Okay? There is a force, right? A muscular force here that's making my arm move away from it, from the other one, right? But then there is another important. Think about another important example. Yes. Huh? I can't hear you. Train. Well, let's see. The trains are connected to each other, right? And then suddenly they move away from each other. Uh huh. Well, they are pulling each other, right? They- Well, they're moving in the same direction, right? Yeah, but they move away from each other. Yeah. Oh, okay. So maybe that's a solution. Maybe you want to tell me. Yeah. What? Which one? The machine. Yeah, the weight, right? They're moving. Yeah. Yeah, but think about that. Just like the weight machine, in this case here, for instance, initially I have a force, right? Initially I have a force. But after, I still am applying a force, right? So that's not a good example. Because the net force at this very moment is zero, right? But after they lose contact, I'm still applying a force for this arm of mine to move away, right? So that's not a good example. It's the same thing of the weight machine, right? I'm gonna tell you. It's gonna be, yeah. What's that? Oh, yeah, that's a good one, right? Yeah, that's a good one. Which other one? Huh? Bumper cars. Let's see. Yeah, you can say that. You can see that there is some. Yeah, but they are not at rest initially, right? They're not at rest initially. They came into collision and they bounce out. In the case of his said the rocket stage, right? The two rockets, even though the whole rocket is moving, right? The two parts of the rocket are at rest with respect to one another, right? Right? So it would work. But then someone else raised their hand, right? What's that? Okay, the other example I can tell you is just the gun. A gun and a bullet. The bullet is at rest with respect to the gun. Okay? And then we have this chemical reaction in the gunpowder that make them move away from one another. Make sense? Okay? The force that the gun is applying to the bullet is in one direction. The force that the bullet applies to the gun is in the other direction. That's why you have the recoil from the gun. Okay, many movies show that. Some movies don't show the recoil. The guy firing the gun and, it's just like he just fired the gun and nothing happens. Okay, but you gotta hold the gun, right? There is a recoil on the gun. So what's that? It's the gunpowder here that's propelling the bullet in one direction, and the bullet is propelling the gun in the other direction. Okay? That would be the example of an explosion. What I call an explosion. And the treatment, mathematical treatment is very similar. Okay? The mathematical treatment is very similar than the other one. Okay, let's do that quickly. Okay, another example, explosions. Example. That's example one, right? What is the initial momentum in this case? What's the initial momentum of this system? Let's go back to the drawing. What's the initial momentum here? Here you go. What's the initial momentum here? Zero, right? And yet, the particles, they are moving away from one another. Why is that they're moving away? Where did they get that energy to move away from one another if they didn't have any energy at the beginning? The energy that they got was from the chemical explosion of the gunpowder. Okay? That's where they got that energy. But momentum is still conserved. Momentum is still conserved. Let's do that. Here we go. Example 1, example 2. Let two masses of same value at rest. At rest, okay? We can picture in another way. Just get the two masses attached to a spring. Okay? Go ahead, compress the spring, lock the spring in place. Okay? Can you picture that? Lock the spring in place. Somehow you lock the spring in place, and somehow you take away the tension in the spring. What's gonna happen? The spring is gonna stretch. It's gonna propel one mass in one direction. It's gonna propel the mass in the other direction. That's another way to look at it. Okay. So here we go. Let two masses of same value m be at rest. That is a chemical reaction. such as an explosion. Let two masses of same value at rest and attached to each other. There is a chemical reaction, such as an explosion, that propel both masses in opposite direction. Okay. Let's see how I'm gonna do that. Find you know find the speed of one mass. I'm not asking the actual speed. I'm asking find the speed of one mass with respect to the other one. Okay. Find the speed of one mass with respect to the other one. Okay. Because the two masses is at rest, not because we have conservation. Okay, because we have conservation of momentum, because momentum must be conserved. Must be conserved. We have initial moment is equal to final moment. Okay, but let's not forget that the two masses are at rest, right? Consequently, the net initial momentum of each mass must be equal to 0. Furthermore, so we are left with this equation here. You know what? Let me ask something. Let me put something else. Let two masses of the same value m be at rest, and attached to each other. Propel both masses in opposite direction. Find the speed of the second mass of. Okay, let's put it this way: of the second mass, not the speed. Find the velocity of the second mass with respect to the first one. With respect to the first one, right? That's what we want. Initial momentum is 0 because the two masses are at rest. And now we have this equation here in which the momentum of the first mass is equal to minus the momentum of the second mass. Okay. We could have done without substituting MV, right? We could have done something like that. Here you go. We could have done this one here because we know they are at rest. And then we could have found that the momentum of the second mass was equal to minus momentum of the first mass. Okay, like that. Something like that. Okay, or, you know, something like that. We can solve now the masses cancel out, right? You go. M cancels out this M. M on the left side cancels out this M on the right side. And VF2 is equal to minus VF1. I do not know the exact value of those velocities, but I do know that the velocity of one is going to be minus the velocity of the other one because they have the same mass. To find the exact speed, you have to know how much energy that gunpowder, provided to those two masses, okay? Remember, I just asked you what is the relative velocity of the second one with respect to the first one. I didn't ask you the exact numerical value. Okay, find the velocity of the second method with respect to the first one in the opposite direction. Okay, that's 5:55. Let's take attendance here. Excel. Okay, Daniel Abraham, are you there? No. Mario Acevedo Jimenez? No. Harun Atif? Musa? Genesis Bell? Nope. Jennifer Camarillo? There. Vincent D'Aloisio? Vincent, not here? Robert Faust? He's here. Okay. Pedro Flores? Next, Lawrence Flores? Alexander Garcia? Sung Ham? No. Ryan Herrera? No. Brian Inies? Athena? There. Jesus Lep? No. Cassandra Martinez? Dylan Martinez? Henry Martinez? No. No Henry Martinez. Leonardo Melgar? No. Rafael Mercado? Raymond Miramontes? No. Jaime Mondragon? Alexis Negrete? Marco Antônio Partida? Armando Pérez? Abraham Pérez? No. Nicolas Pisano? Ramon Quintana? Albert Ramírez? Ali Ferabi? No. David Trompactli? Antônio Veiga? Kenneth Villagomez? Patrick Villalvazov? No. Nolan Williams? Nolan Williams? No. And we are done here. Let's go to our break, 5:57, right? Yeah, let's go to 6:15. Right, break to 6:15. Break till 6:15 p.m. Okay, let's go. Okay, break. So here you go. So we have the situation. Now let's calculate the let's calculate the kinetic energy. Let us calculate the kinetic energy in both cases. Here you go. Calculate the kinetic energy in both cases. Okay, solution, right? First case, calculate the initial the initial and final kinetic energies for both cases. Here you go. First case, initial kinetic energy. Here you go. That's what. Let me get this thing here. I'm gonna copy all of that because I'm gonna need it. Here we go. Initial kinetic energy is going to be what? Is going to be initial kinetic energy of 1 plus initial kinetic energy of 2. Alright. Initial kinetic energy of 1 is going to be half of mv naught 1 squared right, v naught 1 square plus half of m v naught 2 square, v naught 2 square. But we do know that v naught 2 is 0, so there is no kinetic energy for this second mass. That's the initial kinetic energy. What about the final kinetic energy? Final kinetic energy is what? Final kinetic energy of 1 plus final kinetic energy of 2. V final 1, V final 2. But V final 1 is equal to V final 2. Consequently, we have, let's do one more step, right? Because of the inelastic collision, right? V final 1 is equal to V final 2. And we end up with mv final 1, which is what? V final 1 is, I'm going to put here parentheses, is going to be V naught 1 squared divided, oh no, sorry, no, it's just V naught 1. Okay, V naught 1 divided by 2, the square goes outside the parentheses, right? Here, the square goes outside the parentheses, and we finish this calculation by finding out that the final kinetic energy of this system is 1/4 mem v naught 1 square. Okay, compare the final with the initial. You go. Final kinetic energy is less than initial kinetic energy. is less than initial kinetic energy, which is equal to what? Half mv naught 1 square, right? So in conclusion, there is no conservation of energy. There is no conservation of energy during an inelastic collision. Okay. Second case. Second case is a special case of inelastic collision. Okay, second case is explosion, right? Explosion, which is the reverse of a inelastic collision. Okay, so second case, both masses are at rest. Consequently, the initial kinetic energy is zero. There is no kinetic energy whatsoever. The final kinetic energy, those both masses are moving away, and they are moving away with the same velocity, same speed, not same velocity, but same speed. It's opposite velocities, right? V final 1, V final 2, right? V final 1 ends up being equal to V final 2, although it's negative. Wait a minute. I'm gonna put it like this way. It's like that. Here you go. Like that. V final 2 ends up being equal to minus V naught 1. No, wait a minute. Minus V final 1. We do not know the actual value. The actual value of the final one is unknown, right? Because we need to know how much energy is spent. What else? So what we end up getting? We end up getting that this term here ends up being equal to the other one, right? So here you go. When you square a negative, we get a positive and mv final 1, like that. So in this specific case, final kinetic energy ends up being equal, ends up being greater, not equal, greater than initial kinetic energy. Where that energy came from? It came from the burning of the potential energy of the gunpowder, the chemical potential energy of the gunpowder. Okay, so what time is that? 6:28. Let's go another 15 minutes. Okay, now we're going to do the more generic case, the most, those are the simplest ones that you're going to see out there, okay? But let's do the most generic case for inelastic collision. Okay? Most generic case, that's, how are we going to do that? Masses, different masses, both with the same initial velocity. No, not the same. Both with initial velocities different of 0. Okay, example. That should be example 3. Let M1 and M2 having V naught 1 and be moving. Okay, be moving. Let M1 M2 be moving with V naught 1 and V naught 2. Find their final velocity after colliding inelastically. Inelastically. Solution. Let's see if I have another slide here. Okay. Yeah, that's repeating what we have, right? Okay, now it's elastic. Okay. Let me see if I have another one. P30, maybe this one has it. More. Let's see if I have it or not. I gotta organize this thing, I have so much of it. Even I get lost and it's difficult to find what I want to find. It takes a long time. Let's see. Okay, it must be here. Okay, we have this one. We did this one. Okay. Yeah, that's elastic. Yeah, they don't have the... I don't have the most generic. Okay, let's do that from scratch. I don't have a drawing, so but it's similar to that. It's one-dimensional collision, inelastic collision. Okay, don't forget this is one-dimensional inelastic collision. What we did was the lowest. Here go. Let's document it. Summarize here. You know, collisions in order of difficulty. Okay, here you go. Inelastic collision between two masses of same value, two masses of same value, one at rest, and the other moving. Inelastic collision. Oh, there is more. One-dimensional inelastic collision between two masses of same value, one at rest, the other moving towards the other. One at rest. That's the easiest type of problem that you're going to see out there. Then you can have one-dimensional inelastic collision between two masses of same value, both one at rest and the other moving towards the first one. One-dimensional inelastic collision between two masses of same value, both moving towards each other. Towards each other. Okay. What else can you do that? Here you go. We can also have something like the following: one-dimensional inelastic collision of two masses of different value. Okay, that would be another level of difficulty of different values. One at rest and the other moving towards the first one, right? And then you can have the most generic case that I'm going to do right now: one-dimensional inelastic collision of two different masses, both moving towards each other. Don't forget that we still have to treat two-dimensional collisions. We didn't even scratch the surface. We're just talking about one-dimensional collision here. Okay, so those are the possibilities. What we're going to do right now is this one here. We're going to skip the other one. We're going to skip this one. We're going to skip this one. Okay, let's do this one. Most generic case. Item 4. Item 4 of inelastic collision. Both with different initial velocities. Okay, so let's go ahead and let's get our equations. I'm gonna use this one right in here. Solution: initial momentum is equal to final momentum. Initial moment of 1 plus initial moment of 2 is equal to final moment of 1 plus final moment of 2. Right? And now, oh, and don't forget, we gotta put mass of 1, right? And then we gotta put mass of 2. That's the difference here. Gotta change this one as well. And we have the same thing on the right side. The only difference is going to be final velocity of 1, final velocity of 2. Final velocity of 2. Given V0, given M1, M2, V01, and V02, find the final velocity. Because the collision is inelastic, Vf1 is equal to Vf2, or let's say Vf2 is equal to Vf1, right? So what you have here changes, not changes, but simplify. And we can go another step because we can put final velocity of 1 in evidence. Okay. Here you go. And we can solve for the final velocity. We can solve for the final velocity. Here you go. that. Here you go. That's the final velocity. Times that, 640. Let's go another 5 minutes. So what I want to do, I want to find the kinetic energy now. Okay? Find the initial and final kinetic energies. Okay, so I'm going to do the same thing. Let's hunt down my formulas here. That's what I want. Go. Okay, go. Final kinetic energies. Go. Up to here is okay. Up to here is okay. Oh, wait a minute. I gotta change here, right? Next. Good. Okay, and I can leave this way. I can, I cannot go. I don't need to go any further than that. What about the final kinetic energy? Okay, here you go. I gotta change that. M1. I gotta change M2. M2. Fine of 1 is the same as, no, fine of 2 is the same as fine of 1, and that's what we did here. That's what I did here, and now I'm going to replace the fine of 1 square here with that value that I found before, 643, right? And it's gonna be a big thing here because that equation is big, right? And here you go. Like that. Here you go. Like that. And let's see how I'm gonna do. Yeah, there is a, let's see if we can go any further than that. What, one more minute? No, we have 6 minutes to go, right? 6:50 that it ends. But you want to start the exam, right? You're anxious to start the exam. Oh, no, not what I want. This one. Let's go. This one. Let's go. Come on, man. Oh boy, why this guy's so slow? Let's see if I can do anything else here that might simplify. There'll be a cross term, M2, M1. Yeah, it's not gonna help at all, right? I'll leave this way. Hey, if you want to play that at home, you can. You're gonna have a V01 square, V02 square. Oh, I can substitute that here too. Yeah, I can substitute that here too. I substitute only at 1. Okay, so wait a minute. Okay, there is one thing that we can do. Okay, what I can do is the following. I can put here parentheses, right? df1 half m1 m2. Oh yeah, here you go. Do you see a simplification here? I see a simplification here. Right? Do you see a simplification here? m1 plus m2, m1 plus m2, right? So let's go to the next one. Here you go. And here you go, like that. I gotta put v final one here. Let's see. Okay, that's v final one square here. Okay. Final one, yeah. And I can simplify. How am I going to write that down? I'm going to write the following like that. And put that here. Yeah, wait a minute. This one cancels. Yep, I can go like that. Okay, that's what we get. Can we do more than that? See, this m1 plus m1 cancels out m1 plus m2 square. So I simplify it. We are going to get a cross term and a regular, regular term here. Let's see if we can do anything else to simplify it. Well, let's leave this way, and then let's compare to our initial kinetic energy. I didn't substitute final here. That's the final. Okay, here you go. Can I do anything? Yeah, just the half. Here I can manage only with the half. Now, okay, I'm gonna expand that. Let's expand that. What time is that? 6:58. We are almost there. Like that. Go. Right. So here go. Like that. Okay, what I want to tell you is that this term here, this final kinetic energy, is supposed to be less than this initial kinetic energy. That's what I mean, okay? It's supposed to be less than this term right in here. We can look into that next time. It's 6:49 right now, right? So we can go home now. And since there is no conservation of kinetic energy, this term here, final kinetic energy, is supposed to be less than this term here. And it's possible to prove that. Unless I made a mistake here, which I don't think I did, we will be able to prove that. We have definitely the first term, m1 v naught 1 square, right? Oh, the m1 is squared as well. We have a half. This m1 squared divided by m1 plus m2 is less than m1. So this term here is okay. And this second term here is also going to be less than this term. The problem is the cross term that we have to look into later on. Okay? So I see you on Thursday. And good luck with the exam today. We don't have a lab. And, in 10 minutes, the exam is going to be available for you all.